Good morning, class. Here's Chapter 9, Systems of Equations and Inequalities, Section 9.6, Solving Systems with Gaussian Elimination. So we've looked at systems of linear equations in 2 variables, 3 variables, nonlinear equations, partial fractions, matrices, and matrix operations, and now solving systems with Gaussian elimination. The objectives are: write the augmented matrix of a system of equation, write the system of equation from an augmented matrix, perform row operations on a matrix, solve a system of linear equations using matrices. So we discussed matrices and what they are. So recall, matrices are classified by their dimension, the number of rows and columns. A matrix with m rows and n columns has dimensions m by n. A square matrix has the same number of rows as columns. The dimension of a square matrix is n by n, and a matrix with only 0 elements is called a zero matrix. The element of matrix minus A are the additive inverses of the elements of matrix A. Here's an example of a matrix. So you have 1 and 2 rows. And 3 columns. So we call it 2 by 3 matrix. It's just an array of numbers, okay? An array of numbers. That's the definition of a matrix. Operation, when it comes to addition, subtraction, is similar to numbers. A plus 0 and 0 plus A is A. 0 is a zero matrix. For example, for this size, 2 by 3, every entry must be 0. That's what we mean by 0 here. A plus minus A equals A minus A equals 0. So the opposite of that, every entry has an opposite. 2 would be negative 2, 7 would be negative 7, minus 5 would be positive 5, so on and so forth. A plus B equals B plus A. We can add two matrices if they have identical dimensions. So I can add the first entry with the first one, the second one with the second one, and so forth. And this is called commutative property. As you know, this is called associative property. A plus B plus C is A plus B plus C. That works for numbers, that works for matrices. The only restriction is the proper dimension. For addition, subtraction, we must have identical number of rows and columns. A summary of matrix addition and subtraction. If A and B are both m by n matrices, then the sum of A and B, A plus B, is a matrix obtained by adding corresponding entries of A and B. The difference of A and B, A minus B, is obtained by subtracting corresponding entries of A and B. The product of a scalar is a number, K a real number, and a matrix A is matrix Ka, each of whose elements is K times the corresponding elements of A. In other words, if you multiply a number by a matrix, you multiply each entry, each element by that number. However, if you're multiplying two matrices, the product of AB of an m by n matrix A, so this is m by n, and n by k matrix B is an m by k matrix and is found as follows. Notice when you multiply two matrices, the number of columns of the first and the number of rows of the second must be identical, and the result, the size for the result, comes from rows of A and columns of B, m by k. And we've gone through that. You can watch the recording. To find the ith row, jth column, element of AB, multiply each element in the ith row of A by the corresponding element of the jth column of B. The sum of these products gives the element of a row I, column J of AB. The product AB can be found only if the number of columns of A is the same as the number of rows of B. The final product will have as many rows as A and as many columns as B. And then I showed you how to use graphing calculator for matrix multiplication, even addition. First, you have to go to matrix editor, define the number of rows and columns, and then enter one by one. Identity property, an n by n square matrix whose diagonal entries are ones, while all other entries are zeros, is called an identity matrix. This is, for example, identity matrix of 2 by 2. If A is an m by n matrix, then im times A equals A times in equals A, which means if you multiply the identity matrix of a proper size by matrix A, and the identity from the left and from the right may be different size because if A is not a square matrix, and that results in A. Remember, 1 times a number equals a number times 1. That's the same concept. That's the essence of the identity matrix. If A is an n by n square matrix, then AIN equals INA equals A. That means the because it's a square matrix, from the left and right, we have the same identity matrix. Now, new stuff, 9.6, solving systems with Gaussian elimination. Matrices and technology. Matrix methods enable calculators and computers to efficiently handle and solve large systems of equations, matrix row transformations, efficient implementation of echelon methods. Given a system such as this one, A sub 1x plus B sub 1y plus C sub 1z equals D sub 1, the second row, we just change the subscript to 2, third 1 to 3, and so forth. Here's what's equivalent. This is a system. This is an augmented matrix. So we write, if we go, it might be easier to see it column-wise. A1, A2, A3, B1, B2, B3, C1, C2, C3. So these are the rows. These are the columns. Okay. And then for the equality, we put a line, and these are the answers or the constant on the other side. So this is called augmented matrix. This is called an augmented matrix where each member of the array, remember, matrix is an array of numbers, is called an element or entry. The rows of an augmented matrix can be treated just like the equation of a linear system. Augmented matrices. Augmented matrices are used to represent systems of linear equations. The system 2x plus 3y minus equals 12, x minus 8y equals 16 is written as. So what you do, you have all the x's, all the y's, all the z's, and the constant. So you put, this is, by the way, 2 times 1, 2, 3, 4. This part, this adds one more, so it's 2 by 4. Okay, so 2 and 1, 3, the first column, 2, 1. The second column, 3 minus 8. The third column, minus 1. There is no z here, 0, z. And then you have a line, and then 12 and 16. So this is the coefficient matrix, this acts like a equality. This is the constant of the solution as the answer to the right. This is an augmented matrix equivalent to this. So we should be able to go from the system to the augmented matrix back and forth, back and forth. Write the following system of equations as an augmented matrix. We want to write this one. It's a system of 2 by 2. So the matrix will be 2 by 3 because of this last column we're going to add. So this is 3, negative 2, negative 2, positive 1, 3, negative 2. So one more time, 3, negative 2, negative 2, positive 1, and the last column, after you put a line here, 3 minus 2. So this is called the coefficient matrix. This one, the last column represents the constants. That's how it works, everybody. So this is in essence x, this is in essence y, and this is the constant. Now for this one, just quickly, and we will look at it with more details. The first column represents x, the second one y, the third one z. So this would be 3 minus 2, 1. This one, everybody, 1x. 3 minus 2, 1. The y's would be 4 minus 1, and I'm going to add 0y. So the second column, y, would be 4 minus 1, 0. The third column for z would be negative 2, positive 1, minus 6. Then we have a line segment, and this constant, this last column, 903. So this is what we have. 3 minus 2, 1, 4 minus 1, 0, 2 positive 1, negative 6, 903. Okay. So each column on the left represents a different variable. So this is the x, this is the y, this is the z. The last column represents the constants. This acts like a equal sign. So if they give us the system, we can go to the augmented matrix. If they give us the augmented matrix, we should be able to go back. So it shouldn't be a big deal, everybody. Very straightforward. Write the system of equations that correspond to each augmented matrix. First and foremost, the variables. If they give you the variables, you have to follow it. If they don't, you can make up your own variables. Sometimes they go with x, y, z. Sometimes they go with a1, a2, a3, whatever that is the case. So for example, here, we're going to go with x and y here, class. So right here, this one is 4x minus 5y equals 15. This is 7x plus 8y equals negative 9. Very straightforward, very simple. let me write X, Y, Z, because we have three columns to the left of this line, or equality line, if you will. I'm going to go with three variables. So this means 2x plus 0y, we don't have to write it, minus 6z equals 3. This one is minus 8x plus 7y plus 3z equals 12. The last one, minus 5x plus 8y plus 4z equals negative 3. And again, I can't emphasize this enough. You have to write the variables that they ask you. Okay? They may ask for a specific variable, everybody. They may. And then you follow that. So I hope everybody is okay with this. Matrix transformation. Row transformations resulting in a matrix of an equivalent system for an augmented matrix are. Whatever we do to equations, we can do to rows. Number one, any two rows may be interchanged. We can interchange, let's say, equation 1 and equation 2. The elements of any row may be multiplied by a non-zero real number. Remember, if you have an equation, you can multiply both sides by any number as long as it's non-zero, because if you multiply by 0, if it's a 0, it doesn't mean anything. It has to be non-zero. You can multiply both sides by any number, 5, 10, negative 1/2, you name it. Any row may be changed by adding to its elements a multiple of the corresponding elements of another row. This is really the concept of addition or elimination when we solve systems. You can multiply an equation by any number and you add it to another one. Remember, we do that to get rid of a specific variable. So you can multiply a row, the entire row, by anything you want, and then add it to another row. Matrix methods to solve systems of linear equations, REF, short for row echelon method, or row echelon form. Apply row transformation to get ones along the diagonal and zeros below the augmented matrix. Or REF, it's reduced row echelon form. This F stands for form. So apply row transformation to get ones along the diagonals and zeros both below and above. This one was below the augmented matrix. That is row echelon form. This is reduced row echelon form. So in the case of a row echelon form, when you have a 1, the bottom ones must be 0. In the reduced row echelon form, when you have a 1 in the column, the top and the bottom both must be 0. Row operations are used on an augmented matrix to solve the corresponding system of equation. Just what we do to equations, we can do them to rows. So for example, we may interchange any two rows. So here's an example of a matrix. If we use this, it means interchange row 1 and row 2. That's the meaning of it. So the second row becomes the first one, and the first one becomes the second one. So this is an equivalent augmented matrix because as far as the equations are concerned, this is equation number one, this is equation number two, or vice versa. You say this one is equation number one, this one is equation number two. It makes no difference, everybody. Therefore, row one and row two were interchanged. Second one, replace a row by a non-zero multiple of that row. In this case, what are we doing? We are saying row 2, R stands for row. Row 2 is minus 2, row 2. It means just multiply this one by negative 2. That's all it says. Multiplied by negative 2. So what we are going to do, we're not going to change this. We're going to repeat 4 minus 5, 15. This one we're going to multiply by negative 2, but you have to multiply everything by that. So negative 14, negative 16, positive 18. So you multiply by negative 2, and it results in negative 14, negative 16, negative 18. It's pretty straightforward. Every entry in row 2 was multiplied by negative 2. Replace a row by the sum of that row and a non-zero, and that's the key, non-zero multiple of some other row. So we are going to replace the R1 and make the new R1 by multiplying it by 4 and add R2 to that, which means multiply each element by 4 and add the bottom. So this would be, for example, 4 times 4 plus 7, minus 5 times 4 plus 8, 15 times 4 plus negative 9. That's the meaning of it. And the bottom row, the second row, is not being changed. So for example, 4 times 4, 16 and 7, 23. 4 times negative 5, negative 28, and negative 20 and 8 becomes negative 12. 4 times 15, 60. Subtract 9, you get 51. And the second does not change. So every entry in row 1 was multiplied by 4, and then row 2 was added to row 1, to row 1. Row operations. Applying a matrix to solve a system of equation is advantageous due to its efficient notation and its ability to systematically organize mathematical operations, resulting in simplified calculations and clearer visualization of the problem-solving process. It makes it pretty easy to solve systems, especially systems of higher order. 3 by 3, 4 by 4, 5 by 5, and so forth. Example 3. For this augmented matrix 1 minus 5, 8, 0, 1, 4, find a row operation that would result in the entry in row 1, column 2 become a 0. That means you want this one to change to 0. It's important to know you can't say I'm going to multiply this row by 0 because you can't multiply by a 0 since you lose the essence of the original equation. Okay, you can't say I'm going to add a constant to every entry. That's not how the equations work. So whatever we do to equations, we do to rows. So we want to find a row operation that would result in that. Notice if we multiply this one by 5 and add it to -5, it gives us 0. Therefore, you're going to say R1, this is a new R1, is 5 row 2 plus R1. Let's see what happens. So clearly, this becomes 0 because 5 times this and this, they add up to 0. What happens to this one? Because this is 0, it has no effect on this one. 1 remains. But this one, when you multiply by 5, 20, and 8, you get 28. So 5 times 0 plus 1 doesn't change. 5 times 1 minus 5, this changes to 0. Again, remember, you repeat the bottom row. 5 times 4 plus 8. And so this one is 1, 0. This one is 0, 1. This one is 28, 4. We should be able to handle this, everybody. It's not that big of it. And of course, this has to be done pretty fast. Solving systems using matrices. If you look at this example, this matrix is in row echelon form. Notice, and I'm going to remind you of that. This is 1. The first entry is 1, and the rest of them 0. When you go to the second row, the first non-zero entry is 1, the bottom is 0. When you go to the third row, the first non-entry, the first non-zero entry is 1. That's the row echelon form. If it was reduced row echelon form, this would be fine. This one, we have to change this one to 0. This one, we have to change these two to 0. That's a reduced row echelon form. So reminding you, a matrix is in row echelon form when the entry in row 1, column 1 is 1 and zeros appears below it. The first non-zero entry in each row after the first row is 1. So after the first row, the first non-zero entry is 1. 0 appears below it, and it appears to the right of the first non-zero entry. Any rows that contain all zeros to the left of the vertical bar appears at the bottom. So if you happen to, this is the bar left of them. If we happen to have zeros, those 3 are zeros, has to be at the bottom. So these are examples. Notice the first one is 1, and below it is 0. The next row, the first entry is 1. Same thing here, 1, below it 0. The first entry is 1. First thing again, 1, below it 0. And notice these are all zeros, but it's at the bottom. This one, the first entry is 1, the rest of them 0. The second row, the first entry is 1, the below is 0. It happened to have the top is 0 also. The next one, okay, the first non-zero entry is 1, below there is nothing, above is any number is fine. That's why it's not reduced row echelon form. If by any chance these two were zeros, then we would say it's a reduced row echelon. The following examples are not in echelon form, everybody. Let's see why this is the case. We look at part A. Matrix A does not have all zero rows below non-zero rows. See, you see all zeros is somewhere, but not at the bottom. It doesn't matter which row. If it's not at the bottom, it's out. This is not in row echelon form. Matrix B is not in row echelon form. Matrix B has a 1 in the second position on the third row. For row echelon form, it needs to be the right of the leading coefficient above it. In other words, it should be in the fourth position in place of 3. If you look at this one, this row, okay, 1 and the bottoms are 0. That's good. This one, 1 and the bottom is 0. Very good. When you go to this one, this must be to the right of this one, but it's to the left of that. So that makes it not in the desired form. Matrix C has a 2 as a leading coefficient instead of 1. If you look at the first row, 1, that's good. Below is 0, that's good. The second one, the first entry must be 1, and it's not. Matrix D has a negative 1 as a leading coefficient instead of 1. If you look at the first one, 1, and below is 0, that's good. The first row is good. The second row, the very first non-zero entry is not 1. Whatever it is, it happened to be negative 1, not acceptable. So that one is not in the desired format either. By that, we mean the row echelon form. Okay, everybody. So just to make sure it's clear to everybody. Solve the system by the row echelon method. By the way, ultimately, when the system is of high dimension, you can use calculators, but you need to know how the process works, and that's what we want to discuss. So having said that, 5x plus 2y equals 1, 2x minus y equals 4. In essence, row echelon form is the method of addition or elimination, okay? So first and foremost, we're going to write the augmented matrix 5, 2, 2, negative 1, 1, 4. Coefficient matrix, constants. Remember, this line segment acts as an equality. So if you want to go with the row echelon form, the first entry must become 1. That's the purpose. So we want to make this one 1. There are different ways of doing that. Normally, we try to avoid fractions, but sometimes that's the fastest way. If I multiply everything by 1/5, by everything I'm in the first row, I get 1 here. Or if I multiply the second one by 2 and subtract it from 5, I get the same thing. So for the sake of argument, if we multiply this one by 1/5, that means don't change the second row. This one becomes 1, this one 2 over 5, this one 1 over 5. The next step, so the way the row echelon form, if you want to do this process right, you make the first entry 1 and everything underneath 0. And when I say everything underneath, there's only 1 entry. But let's say you have 5 more rows. Who cares? First, you make this one 0, this one 0, this one, all of them 0. So we're going to make this one 0. In that order. After you're completely done with the first column, you move to the second column. And the very first thing is that you make this one 1. then everything underneath 0. We are talking about row echelon form. If you want reduced row echelon form, the top must be 0 also. Then you move to the next one, and this you make this one 1, and everything underneath 0, and so on. So we made this one 1. The next one is to make this one 0. And again, remember, you can't say I'm going to multiply this by 0. That's unacceptable because you can't do it too. You can't say I'm going to multiply the equation by 0. You can multiply this equation by any number you want, except 0. And so how do we make this 2? Notice if I multiply this one by 2 and subtract it from this, that means negative 2 row 1 plus row 2, make it to as a new row 2. This 2 goes away and becomes 0. So minus 2R1 plus R2 will be the new R2. That's what's going to happen, everybody. What does it mean? The first row, just write it. 1, 2 over 5, 1 over 5, don't change it. 2 becomes 0. What happens here? Okay. If I multiply, so I'm going to show you, I'm going to multiply this one by negative 2. So I get negative 4 over 5. Okay. And then I'm going to add it to this one. That means minus 1, which makes it minus 9 over 5. So this one is 1, this one is 2 over 5, this one is 1 over 5. We got 0 here, and we got negative 9 over 5 here. What about here? We're going to multiply this one. So I'm going to show you for this entry now. I want to show you what happens to this one. Minus 2 times R1 minus 2 times 1 over 5 plus 4. Minus 2 over 5 and 4 is 20 over 5. They add up to 18 over 5. And that's what we get here. You have to do this in your head pretty fast, okay, everybody? I'm going to erase my work. And the next one is to make this into a 1. The best course of action is to multiply by its reciprocal. What do you multiply? Every entry in this row you multiply by negative 5 over 9. And you write, so you want to make this one 1. And you are going to say minus 5 over 9 R2 will be the new R2. So this doesn't change. We are just dealing with this one. And this one, 0 times any number is 0. This one, when you multiply it by the reciprocal, becomes negative, becomes positive 1. And if you multiply this one by this one, 5 and 5 cancel each other. Minus 18 over 9 results in negative 2. So this changes to negative 2. This changes to 1. Minus 5 over 9. Maybe I show you. So this one, minus 5 over 9 times this one, 18 over 5 is minus 18 over 9 or minus 2. That's how you get that. Now, this means 1x or simply x plus 2 over 5y equals 1 over 5. This means 0x, we don't write it, plus 1y or simply y equals minus 2. So this gives you y minus 2. Now you do the back substitution to solve. That means put this back into that. So you get x plus 2 over 5 times negative 2 equals 1 over 5. As you know, this is negative 4 over 5. Move it to the other side, becomes positive 4 over 5. And they add up to 1. So the answer is 1 comma negative 2. And you must check. So you go back, so must check. How do you check it? If you put this into the original equation, 1, 5 times 1 is 5, 2 times -2 is -4. Do they add up to 1? Yes. 2 times 1 is 2, minus -2, that means plus 2 is 4, yes. So it literally takes you a split second to check, and you must. So this is done by hand, and we are done. We are going to look at the same question, everybody. But I want to remind you how to use a graphing calculator. Solve a system by the row echelon form. First, remember TI calculator, how to enter matrix. You go to matrix editor. Matrix editor found by pressing second x to the power of -1. Use the arrow key to the right to edit. The very first thing you put the dimension, put all entries. In other words, this is the, by the way, this is the augmented matrix. Everybody remembers that. So you are going to go, and when you go to matrices, it may have some dimension. This one you change. What do you change it to? In this case, 2 rows, 3 columns. First, you change it to 2 by 3. It gives you the matrix, you put it in. Matrix A was originally 4 by 4. You edit it by changing the size, dimension, and inputting everything. Then you go to math. And when you go to math, down here, this says REF, row echelon form. This is the A part. And I'm explaining here, A is REF. So you got to put REF matrix A. That means pressing second x to the power -1, enter, brings up matrix A. So REF matrix A will give you this. And that's the same answer that we had before, but it's in decimal format. It doesn't matter. However, you can go to math and arrow fraction and changes every decimal to a fraction. So this, it changes to the format that we had in the previous case. I hope you remember 1, 2/5, 1/5, 0, 1 -2. That was the first row. This was the second row. Okay. And you do back substitution and you solve it. Now, if you see A is REF, if you go down, the next one, B is RREF, reduced row echelon form. If you do RREF, this gives you an identity matrix here, and this last column is the solution. As you recall, the solution was 1, -2. So RREF will give you the final answer. And again, as it gets more involved, normally you use graphing utilities, but you need to understand how it's done and be able to do it on your own. So we want to solve a system by row echelon form. So we are going to write the augmented matrix. And to write the augmented matrix, the first column would be 1, 3, 1. Second column would be -1, 3, 3. The third column would be 5, -1, 2. If anything is missing is 0, okay? And the last one, the constant would be -6, 10, 5. And we have a line segment in between that acts like a equality. The first step is to make this one 1. It is 1. You don't have to do anything. So this one, we want it to be 1. It is. So we go down the column. We make these 2 0. So how do we make him 0? Well, for this one, if I multiply this one by 3 and subtract from it, that means negative 3R1 plus R2 gives me the new R2. For this one, simply multiply this by negative 1 and add it to this one, or simply R3 minus R1, either way. So minus 3R1 plus R2 gives you new R2, makes this 0. And minus R1, just multiply this by negative, add it to this, gives you what you want. So just as an example, you write the first one doesn't change. Let's see what happens here. If I multiply this one by 3 and subtract it here, it becomes 0. If I multiply it by 3, becomes minus 3. Subtracted from here becomes positive 6. 3 times 5, 15. Subtracted here becomes minus 16. Multiplied by 3, minus 18. Subtracted from 10 becomes 28. This one, just subtract this row from this row. This becomes 0. 3 minus minus 1 is 4. 2 minus 5 is negative 3. 5 minus minus 6 is 11. I hope you can see that. A quick recap. See, this one, if you multiply by 3 and subtract it from this is 0. Multiply this one by 3 minus 3, subtract it from 3, you get positive 6, and the rest of them. Now, so the first step, make this one 1. The second step, make this one 0. The third step, make this one 0. And you could do that in one shot. The next step is to go to the next column, and very first thing, you make this entry 1. That's your first step. Now, just for the sake of argument, if you want to use this row to do something here, because this is 1, it's going to mess up the 0 that you worked hard to get it. You have a choice. You may use the bottom row to do something here, or just multiply this one by what? Divided by 6, or multiplied by 1/6. So the first row and the third row don't touch. This one is 0 because divided by 6 is 0. 6 divided by 6 is 1. Minus 16 over 6. That's negative 8/3. 28 over 6. 14/3. So divide this second row by 6. So look at the first column, we are in good shape. Look at the second column. 1 is good. If we want row echelon form, this is not good. We have to change this into a 0. So the next step is to make this guy 0. Now, if I use the first row, because this is 1, I'm going to mess up the 0 that I worked hard. I can't. But in order to make this one 0, I can use this row, multiply it by 4, and subtract it here. So minus 4 times row 2 plus row 3 makes this one 0. And doesn't get rid of this. So the first row doesn't change. The second row doesn't change. 0 of the third row doesn't change. 4 of the third row goes to 0. Let's figure out this one. I want to figure out this one. So to figure out this one, we are going to multiply this one. We are going to multiply this one by negative 4. So we have minus 8/3 times negative 4. So you see what happens. It's positive 32/3 and added to negative 3, which is 9/3, which is 23/3. So this entry, everybody, 9/3, which is 23/3, 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 9/ is 23/3. What about this one? We're going to multiply this one by -4. -4 times 14/3. So this one multiplied by -4, you get minus 56/3, and then add it to 11, which is 33/3. And we get -23/3. See that? -23/3. That's how you work it out. Um, again, by hand, it could get a little bit, involved. But anyways, let me erase my work. So I hope everybody is clear as to how we arrived at those answers. So one, all of them zero, we are in good shape. One below is zero. This one is not good. This one, we have to change it to one. And it's easy to see how you do that. Just multiply by its reciprocal. Multiply everything by the reciprocal. These two don't change. This becomes +1. This becomes -1. So row echelon form is done. If you were to do reduced row echelon form, you make this one 0, and then you make these two entries 0, and this would be the answer. But for now, row echelon form, this means x minus y plus 5z is -6. This doesn't do anything. Y minus 8/3 z equals 14/3, and z equals -1. So you have z equals -1. You put it here. Negative times negative makes it +8/3. Take it to the other side and subtract, gives you 6/3. So just for the sake of all, I'll show you this one. So for this one, everybody, I'm going to write 1 minus 8/3 times -1 is +8/3 equals 14/3, and you subtract it, you get 6/3 or 2. So we have -1 for z, 2 for y, put it in there. So we have z equals -1, y equals 2, and over here x minus y, which, let me use a different color. X minus y, which is 2, plus 5z, plus 5 times -1 minus 5 equals -6. And -2 minus 5 is -7, goes to the other side. +7 with -6 becomes 1, and these are the answers. 1, 2, -1. Let me erase my. So you can easily find all of the solutions. And if we were to use technology, as it's been mentioned, let me erase my. As it's been mentioned here, you have the matrix A, this one, the augmented matrix. If you do RREF, the last column, everybody, is the answer. If you do REF, it gives you a similar. By the way, this is not unique. I want you to know that. Uh, Reduced row echelon form is unique, but row echelon form is not unique because the uh, steps that we took, one may take a different steps and arrive at the same, but these numbers may be slightly different. The result will always be this. Always check. So you're really not done. I can't emphasize this enough. Must check. Must check. With what? Only the original equation. For example, if I check the first one, 1 minus 2 is -1, plus 5 times -1 is -6. The first one I checked, you must check all three. Always check. X plus y plus z equals 6, 2x minus y plus z equals 5, 3x plus y minus 2z is 9. You want to solve it. And at this point, you have enough practice to do it by hand. We are going to use the technology. First and foremost, we need to write the augmented matrix. 1, 2, 3, 1, -1, 1, 1, 1, -2, 6, 5, 9. So we're talking about 1, 2, 3 rows, 1, 2, 3, 4 columns. We put a matrix A of 3 by 4, and we enter the augmented matrix. There's not enough room to show you the last enter. And this is A matrix. Now, if you do REF A matrix, gives you this one. So what is this last column? X, Y, Z. X is 3, Y is 2, Z is 1. Again, I'm going to check it with one of them. You really should check, must check, must check. I can't emphasize this enough. So X is 3 plus 2 plus 1 is it 6? Yeah, the first one checks. And again, it's not done. You have to check with equation number 2 as well as 3. Example 7, solve a system by reduced row echelon form. And here's the system. The very first thing is to find the augmented matrix. So the first column involving X would be 1, 3, 2. The second one involving Y would be 2, 2, 3. The third one involving Z would be 1, 2, 1. And the fourth one is the constant 30, 56, 44. And we have a line segment in between representing an equality sign. You put that into a calculator. REF matrix A results in the following. And this is the solution. Again, see 1x plus 0y plus 0z is 8. That means x is 8, y is 6, z is 10. And you must check. I can't emphasize this enough. So as an example, again, let me check one of them. X is 8, y is 6, 2 times that, 12, and 8 is 20, plus 10 is 30. So the first one checks. Make sure you check all of them, everybody. Solve a system by the row echelon form, and We are going to go with the augmented matrix. Again, the X column 1, 1, 2, the Y column 2, 2, 4, the Z column 1, 3, 2, and the constant 4, 1, 9. So if we were to do this by hand, if you multiply the first row by 2 and put it in R3, notice what happens. If I multiply this by -2 with this one adds up to 0. -2 times 2 with this one adds up to 0. -2 times 1 with this adds up to 0. -2 times 4 minus 8 and 9, it gives us 1. So I noticed that just by looking at it, I want to show you that right here, even without a calculator, I can see that what happens is that the last row is all zeros, except this one. Let's see what it means. It means 0x plus 0y plus 0z. That means 0 equals 1. That can't be. That can't be. The corresponding equation for the last row, 0 equals 1, is a false statement. Therefore, the solution to the system is an empty set. This is phi, is to both represent an empty set. That means there is no solution. If you were to put that into a calculator, would give you this. And notice that this row echelon form is different than ours. If you put REF, the same thing happens. What matters is this. The bottom row, all entries are 0, except the last one in both cases, meaning the one to the right of this line sub, segment. So the equation on the other side. And that means if they're all zeros except this last one, that's an inconsistent system. Couple more things that will help. Notice that row 3 is twice row 1. 2 times that, 2 times that, 2 times that, except the last one. 2 times 4 is 9. No. So if 2 times this row is this row, then it becomes dependent. But 2 times this row gives you the first 3, but not the last one. Again, notice 2 times 1 is 2, 2 times 2 is 4, 2 times 1 is 2, but 2 times 4, which is 8, is not there. The other thing I want to mention, the concept of a uniqueness and echelon form. The echelon form of a matrix isn't unique. Notice what we have, notice what they gave us. The echelon form or row echelon form isn't unique, which means there are infinite answers possible when you perform row reduction because there are various ways of doing the row reduction. However, reduced row echelon form is unique, which means row reduction on a matrix will produce the same answer no matter how you do perform the same row operation. In this case, in order to get to RREF, no matter how you do it, this is exactly the way you are going to end up with. Okay, so that's important to understand and the difference between the two. Again, before we move on, row echelon form is not unique, but reduced row echelon form is. The reason, again, I mentioned it, your answer may be different than the others, but the result is the same. This means no solutions. Solve a system by row echelon form, and so we go with the augmented matrix. And column X is 2, 1, 4. Column Y is -5, 4, -10. Column Z is 3, -2, 6. and the constant is 182, the column for the constant. You want to perform, and you may notice something is happening, and you just follow that. You notice if we are going to multiply this one by -2 and add it to this one. So minus a 2R1, multiply this by -2 and add it to row 3. See what happens. If I multiply this by -2, 4 and 4, I get 0. By -2, I get +10 and -10 is 0. By -2, I get -6 and 6 is 0. By -2, I get -2 and 2 is 0. So what happens is that the last row is all zeros. The final row of zeros indicate that the system has dependent equations. The first two rows represent the system. If you look at this one, 0x, 0y, 0z is equal to 0, that means 0 equals to 0. Remember, it's an identity that is a dependent system, infinitely many solutions, and that's exactly what's happening here. So this you can ignore, and you can work with these two. So just write these two, just the first two. Also, notice that row 3 is twice row 1. If you go to the equation, multiply the first equation by 2, you get the third one, or multiply the first row by 2, you get the third one. Every entry. Remember, in the case of inconsistent, the last entry doesn't work. But in the case of a dependent, every entry, including the last one, works. So 2x, 4x, minus 5y, minus 10y. 3z becomes 6z, 1 becomes 2. So what does it mean if one is multiple of the other one? That means equations 1 and 2 are the same, everybody. This means equation 1 and equation 3 are the same. If I multiply this one by any number, I'm not really changing the essence of the equation. So I'm multiplying this one by 2 to get to the third one. I'm not changing anything. So this is really worthless. It's the same equation. We're going to work on that. And I'm going to remind you how we work with that. You can do it by matrices or otherwise. So we have the first two. And now we're going to write the augmented matrix for the first two, which becomes 2, 1, minus 5, 4, 3, minus 2, 1, 8. Remember, the first entry must be 1. So how do I make this one 1? Because this is 1, I'm going to interchange the first and the second row. R1, when you have double arrow R2, that means interchange. So put this one as the first equation, put this one as the second equation. When you change the rows, that's the meaning of it. Equations 1 and 2, interchange them. That's the meaning. So I have my 1 here. The second step is to make this guy 0. So how do we do that? Well, notice if I multiply this one by 2 and subtract it from this one. So I'm going to say subtract 2 times of the first row from the second row. That means minus 2R1 plus R2 becomes the new R2. That's the meaning of it. So I want to do that, meaning I'm not going to change the first row. What happens to the second row? 2 times 1 subtracted from 2, it becomes 0. 2 times 4 is 8. Subtracted from -5 becomes -13. 2 times -2, it's -4 subtracted subtracted from 3, that means add 4 to 3 becomes 7. 2 times 8, 16, subtracted from 1 is negative 50. So what's the next step? The next step is to change this one to 1. So how do we change this to 1? Just divide by negative 13 every entry of the second row. So minus 1 over 13, R2 goes to R2. Just divide everything by negative 13. And you got the one that you want. So you're going to write x plus 4y minus 2z is 8. X goes away, y minus 7 over 13z equals 15 thirds. So those are the two equations now we have to deal with. If we make it into RREF, that means we make this one 0, it makes it easier to find them, but that's just as good. Okay, so how do you write this? Remember, in this case, we really have to put everything as a function of one of the variables. So what if we make everything a function of z? So if we want to do that right here, y is this to the right becomes positive 7 over 13z plus 15 over 13. So move this to the right and you're going to find y as a function of z. So z is z, y is 15 plus 7z over 13. And now we're going to put that into the first equation now to find x as a function of z. So we're going to use x plus 4y minus 2z equals 8, everybody. We are going to keep the x plus 4 times. We're going to replace the y minus 2z equals 8. So replace the y with this. We are going to multiply this by 4. We get 60 over 13, 4 times 7, 28 over 13z minus 2z equals 8. So we are going to combine these two. And we are going to move this one. To do so, this we are going to keep, this we are going to write minus 26 over 13z. This we want to move it to the other side. And because we want to subtract it from 8, 8 is 8 times 13 or 104 over 13. So please understand 8 is the same as 104 over 13 because we're going to combine it. Okay. So what happens? These two add up to 44 over 13 because you're going to subtract 60. So these two, 2 over 13z You're solving for x, you take it to the other side, becomes negative. So again, see what happened, everybody. This one combined to 2 over 13z positive, goes to the other side, becomes negative. And now you're going to write x is 44 minus 2z over 13. Y is 15 plus 7z over 13, comma z. This is how you represent a dependent system, everybody.